Hello everyone, this is Johnny. In my previous video, I have demonstrated the results of my Minesweeper convolutional neural network model. The video link is provided in the description below. In this video, I will be talking about the architecture for my Minesweeper CNN model. Here is the high-level overview of today's video. First, I assume people who are watching this video already have some background on convolutional neural network, so I will just provide a brief review of the CNN model. If you don't know much about the convolutional neural network, don't worry, I plan to have a series of videos on deep learning in the future in which I will be discussing all the topics in details, including the convolutional neural networks. After the brief review, I will then talk about the CNN architecture for the Minesweeper game. Then I will talk about how I generated the data and what was the input-output processing. I had to design a custom loss function in this project, so I will also talk about that. Finally, I will show the training testing losses versus training epochs in figures. Now let's get started. We typically use CNN for image analysis tasks. And why is that? Because most of the image analysis tasks have a few similar properties, and CNN takes advantage of these properties. First property is that most of the image analysis tasks are looking for patterns, and these patterns are usually much smaller than the whole image, which means when looking for a pattern, we don't need to process the entire image all at once. We can process one region at a time, and as long as that region covers the pattern we are interested, we will be able to detect the pattern. Eliminate the need to process the entire images reduces the number of parameters drastically. For example, let's say the pattern of interest is a cat's ear as shown on the right. Then the cat's ear is typically much smaller than the entire image. So that's the first property. The second property is that we want to be able to detect the same pattern that appear in different regions of the image. So in this example, we will need our model to be able to detect all cat's ears on the image regardless of their relative location of the image. The third property is that subsampling of the pixels will not change how we perceive the object. The image on the lower right is a subsampled image. I remove 4 columns out of every 5 columns and only keep 1 column. Same thing was done on the rows. I remove 4 rows out of 5 rows and only keep 1 row. However, this subsampling did not change our perception of cats in the image. And finally, the fourth property is that after we detect all the patterns, we typically need a globalization at the end. For example, after we detect all patterns about a cat, such as cat's ears, cat's eyes, cat's bodies, and cat's paws, we will need a globalization step to combine all these patterns to form a cat. These are the 4 typical properties of image analysis tasks. Now let's talk about the typical CNN architecture. A typical CNN architecture consists of multiple repetitions of convolution layers and max pooling layers. For illustration purposes, there are only 2 repetitions of convolution layer and max pooling layers, but there can be more. There is usually a full connected layers at the end of a CNN architecture. The convolution layer is designed by property 1 and property 2. The max pooling layer is designed by property 3, and the fully connected layer is designed by property 4. After understanding the properties of a CNN model, now let's talk about the properties of the Minesweeper game. There are some similarities. First, in a Minesweeper game, we are also looking for patterns, and these patterns are much smaller than the entire map of the game. As an example, the 9 tiles that are highlighted by the red squares are a useful patterns which allows the player to make the next move. It's easy to know that the unrevealed tile inside this red square is an explosive tile, so we can mark a flag to it. Minesweeper also had the second property, namely we want to be able to detect the same patterns that appear in different regions of the map. The two red squares highlighted the same pattern in different regions, and we would like to detect both regardless of their locations. Minesweeper, however, doesn't have the third property. Subsampling on the tiles will mess up the game and won't help at all. Also, playing Minesweeper doesn't need a globalization step. Once we detect a useful localized pattern, we can make next move without a globalization step. Because Minesweeper only has properties 1 and 2, we only need the convolution layers, and we don't need the max pooling layers and fully connected layers. Notice that without the need for the fully connected layer is the key to make our CNN model agnostic to the input size, meaning our CNN model can accept input with any size. After understanding the Minesweeper properties, let's talk about the CNN architecture in details. My Minesweeper CNN has 4 convolutional layers. The model details are shown below. I use Keyrach for these projects. The first 3 layers contain 75 of 4x4 filters. Because I want to make my model agnostic to the input size, I didn't specify the first 2 dimensions of the input shape. However, the input had 11 channels, which I will explain later. Also, I need to set the padding parameters to same. This makes sure we don't lose any dimensions after the convolutional layers. The last layer contained only a single 1x1 filter. This was to make sure I didn't lose any edges in the last layer. I used the soft sign activation function, which transforms all real values to between -1 and +1. Lastly, I also designed a custom loss function, the mean weighted square error, which I will also explain later. For data generation, all data were generated using the rule-based AI that I developed earlier. You can check out the video links on how I developed the rule-based AI in the description below. The first step in the data generation was to convert the game window into a NumPy array that was ready to be fed into the rule-based AI. Here is an example of what it looks like after the conversion. Recall that I use number 9 to represent an unrevealed tile and number 11 to represent a flag. After feeding this input array to the rule-based AI, the rule-based AI determined that the next move should be a right-click on this position that is highlighted by the red square. Using this information, I could determine what the output should look like. The output has the same shape as the input. -1 is used to represent the position of a right click, marking a flag or an explosive tile, and +1 was used to represent the position of a left click, opening a non-explosive tile. 0 was used to represent not a next move. The 2 NumPy array on the left are an example of an input-output pair. Once this move was complete, the number 9 that is highlighted by the red square would then become 11. Then the resulting array became a new input. When we feed this new input into the rule-based AI, it will generate another output. In this case, the rule-based AI determined that on these positions, we should be making a left click, which means we are opening these unrevealed tiles. So the output will be look something like this. Everything will be 0 except this location will be +1. I repeated this process until I generate about 90,000 input-output data pairs. Now let's talk about the input data channelization. Input arrays were expanded into 11 channels, with each channel having only values of 1 and 0 and representing one unique number from the original array. This was basically the same as applying one hot encoding to a 2D array and then producing a 3D array as a result. For example, this channel shown in front represents the position of the unrevealed tile number 9. Wherever the original input has number 9, this channel will have number 1. And wherever the original input doesn't have number 9, this channel will have number 0. There are 11 channels in total because there are 11 unique numbers in the original array, 0 through 8, plus a 9 representing unrevealed tiles and an 11 representing flag tiles. Also, I had to design a custom function in order for the model to work. Notice that the true output will always be all 0 except one tile. This one tile can either be 1 or -1. This one unique tile signifies the position and the action of the next move. Intuitively, we would want the CNN model to really learn well on the next move tile. So I multiply the square error of this tile by 500 before I average all the square errors. As an example, let's say if this first array is our true output and the next move is highlighted by this blue square, the second array is the CNN predicted output. I will first compute the square errors between the two outputs, which are shown as the third array. Before I average out the square errors, I first multiply 500 to this 0.25 because this tile is our next move, so 0.25 times 500, and then I add all square errors and then divide it by 480. I divided by 480 because there were 480 tiles. By giving more weights to this next move tile, I could force the CNN model to really focus on learning this next move. Lastly, I plotted the losses versus the training epochs. The one on the left is the custom losses on both training data and testing data over the training epochs. You can see that even though the training losses were still decreasing, but the testing losses were already stable after about 40 epochs. The plot on the right shows the mean square errors over the training epochs, and this basically covers everything that I want to talk about in this video. Before I end this video, let's just watch how the CNN plays the Minesweeper game one last time.